Welcome back. This video is about yield in chemical industry. Now, for every step in a reaction pathway, yield diminishes. Now, the efficiency of a reaction pathway and the waste produced must be considered. Basically, if you're making a little something, you want to make sure that you're making the most that you can at the best possible value. Now, we need to think about two things here. We need to think about theoretical yield and actual yield. We're going to tackle actual yield first, but here we go. The theoretical yield is the mass of product that can be formed if all reactants react to produce products according to the reaction equation. So, theoretical yield is the maximum amount of product that can be formed using stoichiometric ratios of limiting reactant and assumes 100% conversion. As anyone who's ever done high school science in their life will tell you, 100% conversion is a little much to hope for. So, as you may have guessed, actual yield that you obtain will be less because the reaction may reach equilibrium, or the reaction rate may be too slow to proceed to completion in the time available, or reactants and products are lost during transfers between reaction vessels or in separation or purification stages. Basically, occupational hazard. There we go. So, percentage yield compares the actual yield to the theoretical yield and measures the efficiency of the process. Percentage yield is just actual yield divided by theoretical yield times 100 over 1. Basically, it's how we make a percentage most of the time. So this is, alright, I'm going to write again. Oh, so close. Okay, I hope this becomes at least sensible. All we have to think about is part divided by whole times 100. So what we get divided over what we could have gotten by 100. Now, here's a sample question. So it's 30 grams of propan-2-ol was oxidized to propanone using an acidified solution of potassium chromate. The propanone that was distilled from this reaction mixture had a mass of 20 grams. Now, calculate the percentage yield of this oxidation reaction. Now, I'm going to talk through this one pretty slowly. Okay, so first thing we need to do is we need to write reaction for the equation. As my last videos have stated, whenever you place a oxygen-based functional group in a solution of chromates, it will get acidified. Now, you don't have to do the, oxidized, not acidified, it is already acidified. Now, in this case, it's not necessary to write the full reaction because we just care about the one-to-one bit. So, it's got the same number of carbons, so that's it. That's all we care about. Now, use the mole formula to determine the amount of the reactant. Oh look, it's very conveniently 0.5 moles. If I just go back a second, so working out propan-2-ol's molecular weight is 60. 30 divided by 60 is equal to 0.5 mole. Now, use the molar ratio to determine the amount. Oh, because it was 1-to-1. Oh look, number of moles of propanone is 1 times the original 1, which is 0.5, so it's 0.5. Now, use the formula mass equals number of moles times molar mass to determine the mass of the product if all of the reactant reacts. Now, if the whole thing had have reacted, we would have had 58 times 500 gives us 0.5. Why did I say 500? Gives us 29 grams. So the percentage yield is 20 grams, which is what we got, divided by what we could have gotten, which is 29, times 100, which is 69.0%. Okay? Try it yourself. Here, we're trying to make propanoic acid from propanol. Alright? I'm going to put the Jeopardy timer on. after I read the question. This does not mean you have 30 seconds to solve it. It just means you've got 30 seconds to pause the video and attempt it yourself. So 80 grams of propanol was oxidized to propanoic acid using an acidified solution of K2Cr2O7. The propanoic acid obtained at the end of the reaction had a mass of 55 grams. Calculate the percentage yield of this oxidation reaction. All right, Jeopardy timer starts now. Alright, so here are the steps for it. Here we've got the propanol going to propanoic acid. We work out the number of moles of propanoic acid that we we had to start, which is 1.33. We do our molar ratio calculation. It's still a 1-to-1 reaction, so it's still 1.33 moles for the propanoic acid. We could have made 98.42 grams if we were really good, but we didn't. We only made 55 grams, so 55 divided by 98.42 gives us a percentage of 55.9. So, percentage yields in multi-step synthesis. Now, whenever a reaction has many steps, the yield for each step must be considered and has a significant effect on the overall yield. So here, ideally what we'd want is a 100% reaction, but it's probably not going to happen. So here is what I hope is a relatively simple question. Okay, so calculate the overall percentage yield for the preparation of C from A if it proceeds by a two-step synthesis. From A we make B, and from C we make B. From B we make C. And the yield of the first one is 80%, and the yield of the second one is 70%. Now, if you can multiply 8 by 7 together, you can solve this question. So, the overall yield is just what happens when you multiply the two steps together. If we look at it like we have 100 grams of the first one, if we have 100 of A, after we go to B, we only have 80 grams. Because we only made 80%, and to go from 80 grams of B to C, it becomes 56 grams. Another way that you can just look at this is 0.8 times 0.7 times 100. Now, I am about to give you another question, and I am going to put the Jeopardy timer on, and I hope you can do this one in the 30 seconds. Let's go. Calculate the overall percentage yield for the preparation of D from A if it follows a three-step synthesis. A into B, followed by B into C, followed by C into D. The yield of A into B is 90%. The yield of B into C is 80%, and the yield of C into D is 60%. Your 30 seconds starts now. So here, what we have is a little bit of a different thing, where we've got to multiply 3 together, but the thing is, 0.9 times 0.8 times 0.6 is just 43% once you multiply it by 100. Alright? Atom economy. Now, an industrial chemist needs to maximize atom economy as they develop a reaction pathway that minimizes energy consumption, reduces waste, and has a low impact on the environment. Now, a high atom economy reaction, well, here we've got our two reactants, and then they just combine together to make the desired product. A lower atom economy reaction, well, we're swapping out the green square for the red circle, so the green square is now a waste. You might recognize these as addition and substitution reactions. So you can probably tell which ones we are more excited by as organic chemists to have in our toolbox. However, substitution reactions are both quick and dirty, but they're also cheap. That's why we use them a lot of the time. Now, here is a big concept that we are basically never going to touch beyond this. So, atom economy is a measure of mass of atoms that end up in the product compared with the mass of the starting materials. All right. Now, atom economy is equal to molar mass of desired product divided by molar mass of all reactants, or mass of desired product divided by mass of all reactants. Both of them times 100. Right? So what you need to do is have a look at this question. Calculate the atom economy in the production of ethanol from chloroethane. In this process, chloroethane is heated with a solution of sodium hydroxide. The equation for the reaction is this. C2H5Cl plus NaOH gives us C2H5OH plus NaCl. Now, here is me trying to very, very clumsily draw this with my finger on the thing. Now, so our percentage for our atom economy is going to be equal to molecular weight of C2H5OH. Man, drawing this with my fat finger is still infinitely easier than trying to draw it on a trackpad. Oh my god. Okay, so what we have is, we know what the molecular weight of this is. 12 times 2 is 24. Plus 16 for the oxygen makes 40, plus 6 hydrogens is 46. So we could actually just write 46 right there. But then we also need to work out what the molecular weight of all of our reactants is. So here we've got molecular weight is of C2H5Cl plus NaOH. Well, if memory serves, sodium is 23 and chlorine is 35.5, so that is 58.5 plus 46. I'm just doing this in my head, guys. 105. 105.5, roughly. Excuse me if I got this wrong. I refuse to do a second take. These videos are taking 20 minutes apiece. Now, that's ballpark about 40%, right? Yeah, 104.5, fine. Gold FM. Okay, so that's how we work out the atom economy. 44% is basically what we did. So only 44% of our reactants are actually converted into products. That's bad, right? It's pretty bad. Here's a question for you to give it a try. Calculate the percentage atom economy of the formation of 1-iodopropane from propanol. The equation for the reaction is that. Now, there is no way you can do this in 30 seconds, but I'm still going to put the Jeopardy timer on because I love the Jeopardy timer. Feel free to pause it. Alright, so calculate the molar mass of the reactants. When you add all the molecular weights together, you get 308. The molar mass of the total product is 170. 170 divided by 308 is 55.2. This is the homework. Read chapter 11, complete all the key questions, and if you have the checkpoints, Jesus, I hadn't seen that meme, but I like the meme. It's pretty solid. And if you are in Cambridge checkpoints, please complete the questions. With that, thank you.